Hi, I'm Irvin, founder of DataSciU and creator of PixeLimit. Following our debut for ConvNet models last year, we are excited today to announce PixeLimit's support for PCA models. PixeLimit is an industrial-strength, no-code infrastructure to design, train, evaluate, and deploy machine vision models, all in the cloud with no local state. PCA, or Principal Component Analysis, is a linear algebra methodology for machine vision. Principal component analysis consists of identifying a linear subspace associated with each object class. For each object class, the training images are converted to grayscale and vectorized. Each image is therefore a single vector. Many vectorized sample images for an object class are inserted as columns in an enormous matrix. So we end up with a set of huge matrices of vectorized training images, one such matrix for each object class. We then apply SVD, the singular value decomposition, to find principal eigenvectors of each matrix. Those principal eigenvectors span a subspace, which is characteristic to the object class. After computing an eigenvector subspace for each object class, a new unknown image can be classified. It is classified by vectorizing it and identifying the object class subspace that it is closest to via cosine similarity. The vectorized image is normalized to length 1, then projected onto each object class's eigenvector subspace. The largest projection determines the object's classification, and the magnitude of that projection relative to the other class subspaces is a measure of confidence for the classification. In PixeLimit, a child can design a custom PCA model in literally 10 seconds and moments later train it on the largest image sets in the world. Unlike PyTorch, TensorFlow, or the cloud frameworks, PixeLimit is the first machine vision framework to simultaneously offer industrial strength, a no-code development paradigm, no local state, but still full design control of your vision model, and finally, unprecedented introspection and visual debugging tools to help improve and debug your vision model. PixeLimit allows work with massive image sets such as ImageNet, with literally millions of training images that you can browse and process without ever having to download them. Unlike ConvNets, the PCA model doesn't require a cloud GPU, only high parallelism on our cloud servers. Much of the functionality is offered free, and basic exercises don't even require a login. In addition to full control, you'll have transparency into the inner workings of your PCA model with powerful visualization and debugging tools. To build your PCA model, select the PCA tab from the top menu. In the Design sub-tab, you'll find hyperparameter settings for your model. There are only a few settings for a PCA model. Use the first slider to identify the number of object classes that your PCA model will identify. Another setting is the expected input size for the model. Training and inference images will be resized to the dimensions you specify. Often, downsampling the input images results in greater accuracy, so consider configuring reduced input dimensions while maintaining the aspect ratio of your intended training set. Scaling down the input size also reduces the computation time for training and inference. For our first example, we'll use the MNIST dataset of handwritten digits, which are already small. We'll build a recognizer to distinguish between images of handwritten digits. Let's start with hand-drawn 1s and 7s, which are often confused by people. So that's 2 object classes. These other controls allow fine-tuning of the number of principal eigenvectors to be retained for each object class in your PCA model. In the Train tab, identify the object classes that your PCA model is to identify. You can use PixeLimit's built-in image sets, such as MNIST and ImageNet, or log in to upload and select your own custom image sets. I'll select the MNIST dataset and the 2 sets of hand-drawn digits, which are the object classes. Use the slider to select the size of your training set. Here you may wish to select less than the maximum so as to leave some images as an independent test set. Then hit Train, and that's it. Your PCA model is being trained at the server. The UI updates you as PixeLimit computes eigenvector subspaces and projection matrices for each object class. Once done, for your intuition, PixeLimit then displays a few top eigenvectors for each object class. These are just a top sampling of the grayscale image vectors identified as principal eigenvectors for each object class, but restored to 2D image form for display. What this means is that the training set for this object class is best approximated as a linear combination of these vectorized images. For the MNIST dataset of simple handwritten digits, the eigenvector images bear some visual semblance to their object class. For other datasets like ImageNet, they may not. If logged in, you can save your trained PCA model for future reuse and sharing. You can then proceed to the Test tab. Use the slider to select the number of test images. PixeLimit will make sure to select a test set that is disjoint from that used to train your model. Click Test, and PixeLimit quickly evaluates your model's accuracy in classifying new images. You can then proceed to the Inspect tab, where PixeLimit will identify any misclassified test images and offer visual intuition as to what may be lacking in your model. Here, PixeLimit is displaying the misclassified 1 and 7 handwritten digits, along with each image's embedding or projection onto each object class's eigenvector subspace. You can see that some of the errors were for ambiguously written digits that a human might also misread. Also displayed are all the principal eigenvectors for each object class, sorted by eigenvalue. You can see that the top eigenvectors are reminiscent of the respective object class, whereas subsequent eigenvectors represent smaller additive components that are not construable by us. The MNIST dataset of handwritten digits was used to create the post office's system for reading handwritten zip codes on envelopes. To build such a recognizer for all 10 handwritten digits, all we would do differently is to select 10 object classes under the PCA Design tab, and then all 10 sets of MNIST training images under the Train tab. Let's now attempt a harder classification problem, distinguishing visually between an airliner and a bird. In the Design tab, I'll set 2 object classes, and I'll configure the input size to 1/4 the size of our ImageNet dataset while maintaining the aspect ratio. In the Train tab, I'll select the 2 object classes from the ImageNet dataset. I'll then select the training size and click Train. As before, PixeLimit builds the PCA model and displays a few top eigenvector images for each object class. This time, the eigenvector images are less visually intuitive. Proceeding to the Test tab, I'll test with a small test set. The results are less positive as this was a more complex visual space. A larger training set or different selections for the model's hyperparameters may yield a better result. The choice of design hyperparameters is a creative aspect of PCA modeling. The Inspect tab then displays any misclassified images with eigenvector subspace projections and principal eigenvectors to guide you as to how to improve the PCA model. Thanks for watching this presentation on PixeLimit's PCA model offering. We look forward to improving our workflows for deployment in real-world applications, such as detecting manufacturing defects. With our configurable no-code workflows for PCA, ConvNets, and our upcoming transformer model, we hope to serve you as the most practical and accurate platform for real-world machine vision applications.